Hello, I'm happy to share you with our work, FuRL, Visual Language Models as Fuzzy Rewards for RL. In this work, we study the problem of using a VLM-based reward to train an RL agent in reward sparse tasks. The task reward is 1 when the RL agent reaches the goal, otherwise the reward is always 0. In each task, we are provided a language description of the task. In this work, we simply use the cosine similarity of the VLM text embedding and image embedding as the VLM reward. There are some challenges in directly using the raw VLM reward in RL. Firstly, the raw VLM reward is usually fuzzy and inaccurate. Secondly, when the exploration is hard, zero task reward provides limited information for the RL agent. Thirdly, inaccurate VLM reward could trap the agent in local minima due to the representation misalignment. We first use an example to show the raw VLM rewards could be noisy. In this example, the robot arm aims to push down the red button. An Oracle policy takes nearly 80 steps to solve this task. From the bottom left figure, we can observe that the raw VLM reward generally increases as the robot arm moves close to the button. However, there are a lot of ups and downs in the raw VLM reward curve. As a result, the noisy VLM rewards are likely to trap the IO agent in local minima. To address this issue, we introduced the fuzzy VLM reward aided RL named FuRL. There are two key components in FuRL. The first component is a reward alignment fine-tuning loss. The second component is the relay RL, which we use to help the IO agent to escape the potential local minima. For the reward alignment part, we proposed a lightweight fine-tuning method. In particular, we use two-layer MLPs to align the pre-trained VLM image embedding and the VLM text embedding. We then compute the VLM reward based on the projected VLM embeddings. To train the two MLPs, we use the margin ranking loss. Optionally, if we have a goal image of the task, we can fine-tune the MLPs before we collected the first successful trajectory. We can use the L2 distance between the current image and the goal image to rank the goodness of two samples from unsuccessful trajectories. When we collected the first successful trajectory, we can use two different loss functions to train MLPs. We denote the samples from successful trajectories as the positive samples, and samples from unsuccessful trajectories as the negative samples. We first rank positive samples higher than negative samples. For two positive samples from the same trajectory, we assign the samples closer to the goal with higher ranks. Without the goal image, our reward alignment loss is triggered after the RL agent collected the first successful trajectory. If the RL agent gets stuck in local minima, we are likely to have zero successful trajectories in the end. In FuRL, we adopt the relay RL as an exploration trick to escape the potential local minima. The motivation is that VLM policies does not solve the problem, but it is sometimes close to the solution. Therefore, we iteratively use the VLM policy and the SAC policy to roll out the trajectory. We train the SAC agent with only the sparse task rewards. When we collected some successful trajectories, we then turn off the relay RL. In our paper, we conduct experiments on the meta-world benchmark. We evaluate our method on both of the fixed goal setting and random goal setting. We can observe that FuRL generally outperforms the other baselines. We also conduct different ablation studies to validate the effectiveness of the proposed components. The results show that all the components are useful. More experimental details can be found in our paper. Here's the takeaway. We address the issue of fuzzy reward in VLM-RL. We use the reward alignment fine-tuning loss to solve the domain shift issue, and we use relay RL to escape the potential local minima to improve the exploration.